Here is the problem. We are given three transfer functions. g1 of s equals s to the fourth plus 3s plus 2 divided by s squared plus 4s minus 3. g2 of s equals 5s plus 20 divided by the quantity s minus 4 times s squared plus 2s plus 4. g3 of s equals s minus 4 divided by the quantity s plus 4 times s plus 7. We need to answer four questions. Which transfer function is proper? Which is stable? Apply the Routh-Hurwitz method to all of them. And finally, write the pole zero representation of g2. Part A. Which transfer function is proper? A transfer function is proper when the degree of the numerator is less than or equal to the degree of the denominator. The relative degree equals denominator degree minus numerator degree, and it must be greater than or equal to 0. For g1, the numerator has degree 4 and the denominator has degree 2. Relative degree equals 2 minus 4, which is negative 2. g1 is improper. The numerator is bigger than the denominator. For g2, the numerator has degree 1 and the denominator has degree 3. Relative degree equals 3 minus 1, which is 2. g2 is strictly proper. For g3, the numerator has degree 1 and the denominator has degree 2. Relative degree equals 2 minus 1, which is 1. g3 is strictly proper. Conclusion: only g2 and g3 are proper. Part B. A quick stability check by inspection. A transfer function is stable when all poles have strictly negative real parts, meaning all poles lie in the open left half plane. For g1, the denominator s squared plus 4s minus 3 is not factored. We cannot tell stability by inspection here. We will need the Routh-Hurwitz method. For g2, the denominator is already factored as s minus 4 times s squared plus 2s plus 4. The factor s minus 4 gives a pole at s equals positive 4. This pole is in the right half plane, so g2 is unstable. No calculation needed. For g3, the denominator is s plus 4 times s plus 7. The poles are at s equals negative 4 and s equals negative 7. Both have negative real parts, so g3 is stable. Even though we already know g2 and g3 by inspection, we will still build the full Routh table for all three to practice the method. Part C. Routh-Hurwitz for g1. The denominator is s squared plus 4s minus 3, a second-order polynomial. The Routh array has 3 rows. The s squared row uses the first and third coefficients, 1 and minus 3. The s1 row uses the second coefficient, 4, padded with 0. For the s0 row, we use the standard formula. The first column entry is the determinant of the 2 by 2 block above, with a minus sign in front, divided by the leading entry of the row above. We get minus the quantity 1 times 0 minus 4 times minus 3 divided by 4. That is minus 12 over 4, which equals minus 3. The first column reads 1, 4, minus 3. We count the sign changes. From 1 to 4, no change. From 4 to minus 3, 1 sign change. Total, 1 sign change. By the Routh-Hurwitz criterion, the number of poles in the right half plane equals the number of sign changes. So g1 has 1 unstable pole and is unstable, confirming what we suspected. Routh-Hurwitz for g2. First, we expand the factor denominator. s minus 4 times s squared plus 2s plus 4. Multiplying out, s cubed plus 2s squared plus 4s minus 4s squared minus 8s minus 16. Combining like terms, s cubed minus 2s squared minus 4s minus 16. Now we build the Routh table for this third-order polynomial. The s cubed row uses the first and third coefficients, 1 and minus 4. The s-squared row uses the second and fourth coefficients, minus 2 and minus 16. For the S1 row, the formula gives minus the quantity 1 times minus 16 minus 2 times minus 4 divided by minus 2. That is minus the quantity minus 16 minus 8 divided by minus 2, which is minus 24 over minus 2 equal to minus 12. The S0 row carries down minus 16. The first column reads 1, minus 2, minus 12, minus 16. Count sign changes. 1 to minus 2, 1 sign change. Minus 2 to minus 12, no change. Minus 12 to minus 16, no change. Total, 1 sign change. G2 has one unstable pole, confirming the pole at positive 4 we saw by inspection. Routh-Hurwitz for G3. The denominator is s plus 4 times s plus 7. Expanding gives s squared plus 11s plus 28. Building the Routh table for this second-order polynomial. The s squared row, 1 and 28. The s1 row, 11 and 0. For the s0 row, the formula gives minus the quantity 1 times 0 minus 11 times 28 divided by 11. That simplifies to 28. The first column reads 1, 11, 28. All three values are positive. 0 sign changes. By Routh-Hurwitz, G3 has 0 unstable poles. G3 is stable, confirming the negative real poles we found. Part D. Pole 0 representation of G2. We need to find all the zeros and all the poles of G2 explicitly. G2 of S equals 5s plus 20 divided by s minus 4 times s squared plus 2s plus 4. First, factor the numerator. 5s plus 20 equals 5 times s plus 4. So G2 has a single zero at s equals minus 4. For the poles, we already have one factor s minus 4, giving a pole at s equals 4. For the quadratic s squared plus 2s plus 4, we use the quadratic formula. The discriminant is b squared minus 4ac, equal to 4 minus 16, which is minus 12. The roots are s equals minus 2 plus or minus the square root of minus 12, all divided by 2. That gives s equals minus 1 plus or minus j square root of 3. So G2 has 3 poles total. Positive 4, minus 1 plus j root 3, and minus 1 minus j root 3. The pole 0 form is G2 of s equals 5 times s plus 4 divided by s minus 4 times s plus 1 minus j root 3 times s plus 1 plus j root 3. Let us recap. We analyzed 3 transfer functions for properness, stability, and the Routh criterion. G1 is improper, with relative degree minus 2, and instable with one right half-plane pole. G2 is strictly proper with relative degree 2, but unstable due to the pole at positive 4. G3 is strictly proper with relative degree 1 and stable, all poles in the open left half-plane. And the pole 0 form of G2, numerator 0 at minus 4, denominator poles at positive 4, and minus 1 plus or minus j root 3. 4 parts done. Routh-Hurwitz analysis complete.